In this question, we're going to graph the curve y equals x over x squared minus 4. Well, first thing we should do is factor the denominator. We get x minus 2 and x plus 2, and we see that we have a vertical asymptote at x equals negative 2 and at x equals positive 2. Next, we see we have a horizontal asymptote at y equals 0 because we have degree 1 over degree 2. The intercepts, so if I let x equal 0, y equals 0, 0 over 0 squared minus 4. And similarly, if I let y equal 0 and multiply both sides by x squared minus 4, I get x equaling 0. So the only intercept will be at 0, 0. Now, using the quotient rule, I get the first derivative is x squared minus 4 times 1 minus x times 2x over the denominator squared. Now that becomes x squared minus 4 minus 2x squared over x minus 2 times x plus 2 quantity squared, which is the same as x minus 2 squared times x plus 2 squared. Collecting like terms, I get negative x squared minus 4, which is negative, and then in brackets x squared plus 4. Now, it's important to note that x squared plus 4 is greater than 0 for all x element of the reals, which means the numerator will always be negative because there's a negative sign in front of that. So this part will always be positive, and with a negative sign in front, we'll always have a negative numerator. Now, our first derivative can never equal 0 because this denominator, as we just said, is always positive. So the first derivative will never equal 0. There's no critical number that way, but it is undefined at x equals 2 and x equals negative 2, which is no surprise because we have vertical asymptotes there. Now, applying the quotient rule on our first derivative, we get this long quantity right here, over x squared minus 4 to the exponent 4. Now, notice we've got x squared minus 4 quantity squared here, and we've got we have x squared minus 4 right here in this second part. So we can actually common factor out the x squared minus 4. There's one there, there's two of them there, and there's one of them there. We can common factor that out, and we'll be left with x squared minus 4 times negative 2x here, and then we'll be left with minus negative x squared minus 4 times 2x here. We had x squared minus 4 quantity squared for our first derivative, so now it's x squared minus 4 quantity to the 4. When I do a little distribution here, my numerator becomes this. But notice that I can also cross out an x squared minus 4 factor here with one of the 4 x squared minus 4 factors here. So I'm left with, expanding out this numerator, I'm left with this over x squared minus 4 cubed, because one of these crossed out with that. Simplifying a little further, I get here, and then factoring, I get 2x times x squared plus 12. Now notice that x squared plus 12 will always be positive, so that means that the second derivative can only equal 0. In other words, the numerator of the second derivative can only equal 0 when x equals 0. There's no value of x that'll make this factor equal 0. And y prime prime is undefined at x equals 2 and x equals negative 2. So our, and again, that's no surprise because there's a vertical asymptote. There's no point there. Now, we should know what the y values are at x equals negative 2, x equals 2, and x equals 0 because they variously made the first and second derivative 0 or undefined, and it's always important to know those y values. At x equals negative 2, y is undefined. At x equals positive 2, y is undefined. At x equals 0, y is 0. Well, we already knew we had the point 0, 0. Now we know it's a point of inflection. And because we had a vertical asymptote, we're not surprised that the y value is undefined at x equals negative 2 or x equals 2. So what we're going to do now is do some interval testing on the first derivative and the second derivative. So the first derivative, if I let x be a number less than negative 2, I get a negative squared and a negative squared, which is positive. This is always positive, but multiplied by a negative, it becomes negative. If I let x be a number in between negative 2, like say 0, I get negative 4 in the numerator. I get a positive denominator, so I have a negative numerator. And finally, if I let x be a number greater than 2, you can sub in a value if you're not sure. You'll get a negative value for y prime. For y prime prime, again, if you're not sure how to do it, plug in a number, but if you plug in negative 3, this quantity is negative. If you plug in -1, this quantity is positive. If you plug in 1, this quantity is negative. And if you plug in a number greater than 2, this quantity is positive. So in summary, what we have in this question is an intercept at 0, 0 that also operates as a point of inflection. We have a vertical asymptote at x equals -2 and at x equals 2 with a horizontal asymptote at y equals 0 with the first and second derivative increasing, decreasing, and concavity drama working like that. So now we're going to try and graph it. Well, we see here that we are going to have a point of inflection here. This is a vertical asymptote, and we see that we're decreasing from -2 to 2, but we're also going through 0, 0. So the curve must be coming through here somehow. But keep in mind that we're concave up. We're decreasing the whole time, but we're concave up from -2 to 0. So that means the curve must look like this. And don't forget, this is a vertical asymptote. We're concave down between 0 and 2, and we're decreasing, so the curve must look like this. And this is our vertical asymptote. Now, to the left of -2, we're going to be decreasing and concave down. Well, you might think to yourself, maybe we're up here somewhere, but that wouldn't make sense because our only intercept was at 0, 0. So we know that since this is a horizontal asymptote, we must look something like this. This curve is decreasing and concave down. In other words, if I drew a tangent line here, the curve would be below that tangent line. And finally, to the right of that vertical asymptote, I'm decreasing and concave up. I can't cross this axis, but it is a horizontal asymptote, so the curve must look something like this. Now, when it comes to horizontal asymptotes, sometimes what people do is they'll pick a number greater than in magnitude any value for x that creates a discontinuity. So the greatest value of x that creates a discontinuity is 2. So what sometimes people will do is they'll pick an x value much greater than 2 and see if the y value is greater than 0 or less than 0. So if we did that with our original equation, which is x over x squared minus 4, if you pick a number for x that's very positive, like say 100, you'll get a number that's very small, but it will be positive. And that'll tell you that when x is 100, your y-coordinate is greater than 0. So you're going to be above the horizontal asymptote. And similarly, you can pick a number far to the left of that vertical asymptote. So if you pick -100, this would be a negative y value, which would tell me that the curve is below the x-axis at that point. So that would tell me that as I approach this curve to the left, I'm approaching the horizontal asymptote from below. So anyways, this is what the curve ends up looking like.